Rao Bhim Chapter 9 Quadratic Forms. Suppose we have n variables x1 up to xn. Then by a quadratic form in these n variables we mean an expression like double summation I and j aij times xi xj, where each of the aij's are real. A typical example will be 5x1 squared, so a11 is 5, 2x1 x2, so a12 is 2, minus 3 by 2 x2 x1, so a21 is minus 3 by 2, and finally a22 is 6. Here I have taken n equal to 2. Now if you look at this expression, you can immediately see that x1 x2 is same as x2 x1, so I might as well combine the two and just say that I have one x1 squared term, one x2 squared term, and one cross product term. Now if I construct a matrix out of all my aij's, then I can write these in terms of a matrix notation by considering all my variables inside a vector, like this. Then this expression may be written as x transpose, the vector lying down, then a square matrix times another vector. So notice the order. This is 1 over n, this is n times n, this is n by 1. So it is a scalar quantity after all. Now because the same term occurs multiple times, this capital A is not uniquely defined. For example, in this case, I could as well have said the following. This is minus 3 by 2. Just combine all of them and you will get a plus half here. And then this can be considered to be 0. So I can say that A12 is half and A21 is 0 without actually changing this expression. I might as well do this. I might make this minus 10 and just compensate by adding the 10 here, so I can make it, if I add 10, 21. So all these things are basically the same quadratic form. Now in order to get a unique matrix, we need to put some further restriction, and the standard restriction that we put is that we will split up the coefficient equally between x12 and x21, in general between xi, xj and xj xi. So in our case we had the total thing was just half, so I will make this 1/4, that is half of half, and this will be the remaining 1/4. So that way my matrix A will be symmetric, and this matrix is now uniquely determined by the quadratic form. Any quadratic form in x1 to xn can be uniquely written as x prime ax, where A is real symmetric. Thus, if we find that x transpose ax happens to be identically equal to x transpose bx, then I can immediately say that A must be equal to B, where A and B both are real symmetric. If we do not have the symmetry condition, then we saw just now, we really cannot say that equality of the quadratic form implies the equality of the matrices. So in this case, we often talk about A as the matrix for the quadratic form. If I ever write a quadratic form, you understand that A is tacitly assumed to be real symmetric. Next we come to a classification of quadratic forms. Some quadratic forms, it will be seen, are always greater than or equal to 0, while some others are always less than or equal to 0. Yet some others can take both positive and negative values. The classification is based on that. Suppose I take this quadratic form. This may not readily look like a quadratic form, but if you do this squaring and this squaring also, you will find that it is indeed a quadratic form. Now the way I have written it, you can quite easily see that for real variables this can never be negative. So this is always greater than or equal to 0. So such a quadratic form is called non-negative definite, and it is abbreviated to NND. Now compare this quadratic form with this quadratic form. Here also you will see that this always has to be greater than or equal to 0, no doubt about that, but something stronger is true. Suppose this is equal to 0, then you can definitely say that x1, x2 and x3, all of them must be exactly equal to 0. So this is 0 if and only if your x vector is just a 0 vector. Here, however, that is not the case. You can achieve 0 even when x1, x2, x3 are not all 0. For example, if this is 0, you can see x1 is negative of x2 and x3 is same as x1. So I can as well take x1 equal to 1, x2 equal to minus 1 and x3 equal to 1 as well. Then also this thing will be equal to 0. So this one is a non-negative in a stronger way, because if I put all the xi is equal to 0, then goes without saying any quadratic form has to vanish. But if even at least one of them is non-zero, this must be strictly positive, and such a quadratic form is called positive definite or PD. That is, it is definitely positive, except of course in that trivial case when x equal to 0, then it of course has to be 0. But if it is non-zero, it has to be strictly positive, while this one is non-negative definite but not positive definite. So understand that anything which is positive definite is also non-negative definite. Now suppose that I put a negative sign here. In that case, my inequality will flip direction, and I will get something which is always less than or equal to 0. You can get that I am going to call it non-positive definite, and it will be abbreviated to NPD. Similarly, if I put minuses everywhere, then I will get something which should naturally be called negative definite. Negative definite. And as before, everything which is negative definite is definitely also non-positive definite. Now you can of course have something which is neither positive negative nor negative definite. Suppose I make one of them plus and the other minus. In that case, you can easily see that you can now make it both greater than 0 or less than 0. You cannot say anything in either direction, and we call such a thing indefinite. Indefinite, that is, it can take both positive value and negative value, and definitely it can always take the value 0 if you set all the xi equal to 0. This Venn diagram is something that you should remember. Here we have all quadratic forms, and now in that we have got two subsets, all my n and d quadratic forms, NND, and all my NPD quadratic forms. Notice that there is a little intersection. In this intersection there is exactly one element, and that quadratic form is the identically 0 quadratic form. That is, all the coefficients are equal to 0. It is both always greater than equal to 0 as well as less than or equal to 0, because it is just equal to 0. Now inside N and D I have a subset which is called PD. So these are my PDs, and here again I have a similar subset which is called negative definite or ND. Everything outside are indefinite, which I will denote by ID. Now whatever is remaining inside this region, that is non-negative definite but not positive definite, there is no fixed terminology for that, but the Rao Bhim book uses the term positive semi-definite. And similarly, whatever is inside this ring-like region, that is NPD but not ND, that is called negative semi-definite. In many books, positive semi-definite is used to mean same thing as NND, and NSD means the same thing as NPD. There is no agreement among authors as to this terminology. But NND, PD, NPD, ND and ID, they are all agreed upon definitions. Now recall that every quadratic form has associated with it a unique real symmetric matrix, and given any real symmetric matrix, I can obtain a quadratic form. So any property of the quadratic form X transpose AX is basically a property of the matrix A. So whatever description I have given applies directly to real symmetric matrices. So I can say this is the set of all real symmetric matrices. Certain real symmetric matrices are non-negative definite, meaning that X prime AX is always greater than or equal to 0. Similarly, non-positive definite. Positive definite means X prime AX is strictly greater than 0 whenever X is non-zero, and similarly for the other things. So all these things may be now used for real symmetric matrices, and we often talk about a real symmetric matrix being positive definite or a non-semi-definite, or negative semi-definite. This entire discussion that we gave is summarized in definition 9.2.1 in the book. It is quite easy to construct matrices, real symmetric matrices of a particular category. If you simply start from a quadratic form, I am using only 3 variables, x1, x2 and x3, then this is of course a non-negative definite quadratic form. Just look at its coefficients. So it will be x1 square plus twice x1 x2 plus x2 square plus x3 square. You can immediately write down the corresponding matrix in the following way. Just consider all these things labeled as x1 x2 x3, x1 x2 x3. Then the coefficient of x1 square, x1 there is 1, coefficient of x2 square is also 1. Similarly for coefficient of x3, coefficient of x1, x2 is 2, split them up over these two entries, x2, x1 and x1, x2, each of them gets 1, no other entry. So here is a real symmetric matrix which is non-negative definite. An even quicker way is to work with just diagonal matrices. So here is one quick positive definite matrix 1, 2, 3, 10, where all these things are 0, and I have used 4 variables x1, x2, x3 and x4. If you want to make it negative definite, just put a minus sign. If you want to make it indefinite, make some of them plus and some of them minus. If you want to make it positive semi-definite, just make one of the diagonal entries 0. So you can very easily construct real symmetric matrices of whatever category you like. A quadratic form, we have said, is something like x prime ax, where a is real symmetry. Now x is an n by 1 vector of real quantities. So I can consider this as a map. X is being mapped to this. In that case, it is a function from Rn to R. So a quadratic form can be considered as a special function from Rn to R. Now notice that once I look at it and in this way, it is basically a vector space, and this is the underlying field. Now this matrix, you will now notice, actually depends on what basis you are using. For example, suppose we are working in R2, then here is a vector. Then this vector is going to be mapped to certain number in R. So this vector will be mapped to something in R. Now how do I express this vector? I express this vector as a pair of numbers depending on the coordinate system I choose. Suppose in this case this vector happens to be 1, 1, then 1, 1 is mapped to this. Now if I change my coordinate system to say this, so this is my new x-axis, this is my new y-axis, and I consider this as my unit length, in that case, of course, the same vector, the same arrow will now have the representation 1, 0, but it is the same vector. So when I consider it as a map from the two-dimensional plane to the line, this should still go to that point, but now I have to say 1, 0 goes to that value. Clearly, this matrix A will now have to change in order to represent the same function. So this is the situation which is much like a situation that we have seen earlier about linear transformations. There we saw that it was like a black box into which you feed a linear transformation. We know that every linear transformation can be represented by a matrix, but with respect to a certain basis. So this arbitrarily chosen basis was causing much of a problem. There the linear transformation was, say, from Rn to Rn, and we were choosing a basis. Now the very similar thing is happening here, except that we are working with not a linear transformation but with a quadratic form, which is a function from Rn to R. But here also, if you change the basis, the matrix representing it, this matrix is of course real symmetric, a special type of matrix, that changes. So if you are trying to look at a property of the matrix, if you are trying to study the quadratic form, you are basically studying the matrix. Now part of the properties of the matrix will come from the arbitrarily chosen basis, while part of the property will come from the quadratic forms. And naturally, you are interested in only those properties of the matrix which will be governed by the quadratic form irrespective of the basis. For this, it is important to know how the matrix changes if I keep the quadratic form fixed but change only the basis. Now we know that whenever we change the basis, that is implemented by a change of basis matrix, which is a non-singular matrix. Every non-singular matrix gives you a change of basis. Now how will the matrix change? Now it is not very difficult to see that the change will be the following. So once I have x with respect to some basis, if I make a change of basis, then in that case this thing will turn into px. We have seen this earlier also in connection with linear transformation. So if with respect to one basis the representation of a vector is given by this tuple, with respect to another basis where the change of basis matrix is P, the new representation will be given by Px. So your matrix now will become X transpose Ax will now become, put a P here and put a P transpose here. So your new matrix becomes P transpose AP. So if you change the basis here, this changes by a P transpose AP transformation. Now this motivates us to give a name to this kind of transformation. We call it congruence. When we say two matrices are congruent, they are both square matrices, same order, we mean that one may be written as P transpose times the other times P for some non-singular matrix P. It is quite easy to check that this is an equivalence relation. Now, as in case of linear transformations, we are interested in properties of a real symmetric matrix that are invariant under this congruence operation. That is, if that property is there in a matrix A, it is also there in any matrix congruent to A. Now we have already seen one set of properties, namely positive definite, non-negative definite, etc. It is quite easy to see that all those properties survive congruence transformation. Suppose A and B are real symmetric matrices and they are congruent to each other, then A is PD if and only if B is PD, and the proof is pretty trivial. You just proceed like this. Suppose X transpose AX, I am showing this side, is always greater than 0 whenever X is non-zero. Now since B is PD, I can write, since B is congruent to A, I can write this as some P transpose AP where P is non-singular. So when I get this condition, I want to show that this also holds. So what I will do is, I will just write X transpose Bx, I want to show this is also strictly positive. This is X transpose P transpose A Px. Just call this Y. So then in that case it will be Y prime A Y. Now can I immediately say that this is strictly positive? Well, I had the condition X is non-zero, but is Y non-zero? Well, it is, because Y being Px cannot be 0 because P is a non-singular matrix. It cannot multiply a non-zero vector and produce just the null vector. So this is also strictly positive. Now, of course, since if B is congruent to A is also congruent to B, so clearly from this we use the same proof in the reverse direction to show that. Now you can easily see that the same argument essentially works for N and D, then it is N and D and everything else. So all those categories are invariant under congruence transformation.